Okay. Getting good at this thing. I think. Well, I could probably do better. There you go. That's the thingy. Haha! Okay. So we're going to be going over 6.1, all the math stuff. Let's just go ahead and do it. We're going to be using integration by parts, remember. That's u times v, some product. U times v minus v times du. We went over this one today in session, so I'm not really too stressed about it. But one thing you should probably remember is something called ILATE. ILATE is an anagram, an acronym is the right word for it, for explaining which one of these two cases you'd probably want to use to be your U and to be your V, depending on which one comes first. The name of the game here is to simplify it as quickly as you can. So, ILATE inverse, logarithmic, algebraic, trigonometric, and exponential. That's what you need to know. So this is neither of the first two, but this is before the trigonometric. So you probably want to pick your algebraic value to be your actual u first. And that's exactly what we do. And then we realize that the derivative of u is just dx. dv is cosine of 5x. Now to just go ahead and go over the integral of cosine 5x for those who just want maybe extra refresher. You would u sub this 5x, du is equal to 5 dx, and thus du over 5 is equal to dx. You apply that kind of idea here, thus you're left with the integral of cosine of u all over 5 to be sine of 5x all over 5. One and done. So just to go ahead and shorten this, v is equal to sine of 5x all over 5. We apply this idea. So x sine 5x all over 5 minus 1/5, because you take that 5x outside, sine of 5x du, or in this case it'd be dx, right? So do that same integration that you did for the cosine earlier, but you apply it to sine. Now this just becomes 1/25, because I'm going to go ahead and take out some unnecessary coefficient when you did the u substitution and blah 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 blah. Basically the same idea that you did for this one. Just go back and look at that video portion. Now sine integral is actually different than what it is in its derivative. The derivative of sine is cosine. Derivative of cosine is negative sine. Those negatives and positives switch when you handle cosine and sine's integrals. Integral of cosine is always going to be a positive sine x. The integral of sine is always going to be a negative cosine. Get that? Good. So x sine 5x all over 5 plus, because of that other negative that comes up, all over 25, and don't forget your plus c. That's how you handle that one. Give you guys some time to take a look at it so that we're on the same page. Alright. Now, computation is difficult, I get that. So let's look at the next one. X squared plus 1 e to the negative x dx. There's two ways of doing this one. You can literally multiply it out. This becomes a integral by parts. This is really easy. Or you can just do it straight up. we're just going to do it straight up because I said so, and I don't want to do the other one. So u, remember ilate, this is the algebraic and this is the exponential. This comes first, so I don't want to have to worry about the exponential here. Right? So x squared plus 1 dx is equal to 2x dx dv e to the negative v. I just want to go over this so people kind of get ready to rock here. U sub negative x is what you choose, so du is equal to negative dx, so du negative equals dx, right? You apply this idea here, negative e to the negative x, by the way this is just e to the u here, du. This is always just going to be, if the integral is e to the u, the answer is e to the u for all that. So v becomes e to the negative x, well, negative e to the negative x. And apply that same idea of trigonometrics by integration by parts. My bad, not trigonometrics, by parts. X squared plus 1 negative e to the negative x plus, and then we have what, 2x e to the negative x dx. Now, the thing we need to do is apply another integration by parts. Again, we have another algebraic and an exponential, making me force myself to work with this one. And I want to force myself to work with this one because there's no way, if we went this way, that you would actually find an integration. Because this would ultimately just continue being either negative or positive of this. And you're never going to satisfy your claim. And you're never going to get your integrand because this is going to become way more complicated and way more facetious to worry about because it's going to be so hard in the long run. So if we come back to this, we say, well, u is equal to 2x, du is equal to 2 dx, v e to the x, dv, my bad, v is equal to e to the negative x, so applying the same idea, 2x e to the negative x plus 2 e to the negative x, so 2x e to the negative x, and then over here we have negative 2 e to the x, right? So x squared plus 1, if you really wanted to, you can simplify it, right? You can go e to the negative x, x squared plus 1, just take out the negative 2 because they all have it, plus 2x, and then plus 2, right? This same thing would just become x squared plus 2x, and over here this becomes just plus 3, and then between 1 and 0, go ahead and apply your mathematics there, 0, 0, 0, 3, right? This just becomes, quite literally, what this has become. Go ahead and write it. Negative 0, 3, this becomes a 3, but then there's a negative right here because you subtract them, so that becomes a plus 3. And then over here, this is to the 0, to the 1, and then this is going to be 1 plus 2 plus 3, so you're going to have 6, so this is going to be minus 6 to the negative first power. In fact, it's minus 6 e to the negative first power. That is your integral for this answer. Take a look-see. Looks pretty good. Okay. Give you some more time to go ahead and just digest everything I said. No pressure. Now, we're going to start going into more difficult ones that at first seem really hard, but they're really not. So, Isabella, Diana, Armando, and forget the next person in your group. My bad, man. This one's not that hard. You guys did excellent on this one, by the way. By the way, Antonio, you guys did good on that one too. Group 1 did good on theirs, and then everything's gonna run smoothly. I believe in it. So theta cubed cosine theta squared. Same idea. Ilate makes things super easy, but I don't want to have to worry about doing integration by parts a bunch of times. I see a potential to make this easy. And what I do is that I u sub theta squared du is equal to theta, my bad, 2 theta d theta. So, theta cubed all over 2 theta cosine u d theta, or du, right? So this gets out of the way. 1/2, I'm ignoring this for now, I'll worry about that when I get there, equals theta squared cosine u du. We're in terms of u, so these can be converted into the respective sign we want. Thus, 1/2 u cosine u du. This is much easier to work with than doing integration by parts 50 bajillion times. I'm exaggerating, but it's still there, right? So now I'm going to just say w is equal to u. So dw is equal to du. dv is equal to cosine of u, and hence v is equal to sine of u, right? So the same thing folds. U sine of u minus the integrand of sine of u, which we know is just going to be plus cosine of u sine of u, plus c, and using what we already know as our past information, theta squared sine theta squared plus cosine theta squared plus c, and we already have our respective bounds, pi over 2. These are actually the ones like this. Very important to keep that notation. Pi times sine pi plus cosine pi. We're only left with one option mathematically. This is 0 no matter what you do. And this just becomes pi. That's funny. Anyway. This becomes 1. Pi over 2 we have as pi over 2 here, right? Sine of pi over 2 plus cosine of pi over 2. This zeroes out, much like this zeroed out. This is a 1, and then this is a pi over 2. So, if we do 1 minus pi over 2, make this all one big fraction, 2 times 2 is 2 minus pi over 2. So, that's, wait a minute, I forgot to add the 1/2, huh? So, times 1/2. Thank you for catching me on that. So your full answer should be 2 minus pi all over 4. But these are the same thing, so it doesn't really matter. Good? Okay. Give you some time to look at it. Isabella, take note of how we actually use the integration by parts in these functions. I know that maybe at first much of you are in Arthur's class, or not in my particular class when we went right into integration by parts. But just to keep this idea alive, the product of two functions, when you integrate it, is when integration by parts is going to be used in some degree, okay? And we need to realize that we want to make things easier, not harder. So we pick, using the anagram or acronym ILATE, which one of these potential functions can be decreasing or potentially simplifying the equation so that when I integrate, I can work with something defined in what we know already. Doesn't matter what it is, just that it is. Right? So go ahead and take a look. Take a look at all the work. Give you guys some time to look at it. Alright? Nothing too hard, you know, and since you guys asked for this, I will be writing more of this material. This is the one that many of you didn't do because I accidentally did not give it to a group, okay? But the thing still stands except this one's different. We're going to use ILATE in relation to this logarithmic function, but this is going to be your u. Trust me on this. So we suppose u is equal to ln cubed x. Then du is equal to u to the third ln x, right? So du is equal to 3 ln squared all over x dx. Does that make sense? And then now we have dv is equal to 1, so v is equal to x. We're going to be doing a lot of integration by parts here. So ln cubed x times x minus 3, multiply these two together, ln x all over x times x dx simplifies. See that right there? So you see, you can also think about using u's and v's in potential simplification. And now you're here. Much like previous problems, where I was asked whether or not I do integration by parts again, this applies here too. So u is equal to ln squared x, du is equal to 2 ln x all over x, dv is equal to 1, so v is equal to x. And when you do this, x ln squared x minus, and then over here 2 ln x all over x times x dx simplifies, and then you would just do the integral of ln of x, and that is actually not that hard again, but you would have to use integration by parts a third time. So u is equal to ln x, du is equal to dx all over x, dv is equal to 1, so v is equal to x. You see that there? Perfect. So then we bring all of this back up because I'm going to work with this integrand right here. I won't worry about this until I get there. ln x times x minus, and then you're going to see that 1 over x times x cancel out to just dx. So x ln x minus x is that integrand. Now we're just going to add everything together and then simplify. So when you simplify everything, you have an x cubed ln x minus 3, and then that 3 is going to be times x ln squared x. So x ln squared x, and this negative 2 is going to multiply all into this, and accounting with this negative 3. So this is going to be a plus 6 x ln x, and in this case this is going to be a minus. So these two were pluses, minus 6x. Okay? And then obviously you're going to have your plus c at the very end of everything. Again, just so everybody knows, x cubed times ln x, so x cubed times ln x minus 3x ln squared x. Oh, my bad, I wrote it wrong. There you go. Let me reiterate that. X cubed times ln cubed x minus 3x times ln squared x plus 6x times ln x minus 6x plus c. Now, we are going to then plug in our values of 2 and 1. So this is going to be 8 ln cubed 2 minus 6 ln squared 2 plus 12 ln 2 minus 12. This is going to be ln cubed 1 minus 3 ln squared 1 plus 6 ln 1 minus 6. These zero out based on ln property. When you put 1 into it, it's 0. And then you have 8 ln cubed 2 minus 6 ln squared 2 plus 12 ln 2, and then this is plus because of the subtraction here. Plus 6 minus 12 is still a minus 6. Okay, so the answer from 2 to 1 of ln cubed x is, if you were just looking for the family of curves, x squared ln cubed x minus 3x ln squared x plus 6x ln x minus 6x plus c. But with the boundaries involved, you're going to have 8 ln cubed 2 minus 6 ln squared 2 plus 12 ln 2 minus 6. Does that look good for everyone? Perfect. I'm going to go ahead and work on the following. You guys had ample time to look at this. If you didn't, well, say lovey. Alright. Maria and Mohammed worked on this one. This one will be great to go over once more. Radical 4 plus r squared dr, I think. Well, we're in luck because much like the previous one, well, the previous one before that one, you had to use a u substitution. And that's exactly what we're going to do here. We're going to suppose u is equal to 4 plus r squared. The derivative just then becomes 2r dr. Right? So then over here, 0 to 1. That becomes, if you do everything together, du 2 all over dr. So we had everything here. You're going to get r squared du, radical u, 1/2. Now, at first it might seem worrisome to have this there. But we kind of have an equation to handle that already. One thing that I think really solidifies what we needed in order to simplify this equation, and that's up here. I realize that 4 plus r squared is equal to u. So I can find out what u is. So I say then that u minus 4 is equal to r squared. So u minus 4 du radical u 0, 1, 1/2. So now I'm going to say, hey dude, can I do integration by parts? And you can. You really can. Say love you. So I'm going to choose u minus 4, or I'm going to call it w in this case. dw is going to equal to du. Now why did I choose this one instead of this one? If they're both algebraic in their design, simple. This is going to simplify to a constant of 1. When you derive it, it becomes just 1 times du. You don't derive this and get that same thing. You get 1/2 radical u. All that is going to be above, this is going to be below 1, which is going to look like 1 over 2 radical u. Right? And I don't want to have to worry about that. So then I say, okay dude, what's next? Well, dv is equal to u to the negative 1/2, implying this is going to be radical u all over 2. Actually, wait, hold on. This is going to be 1 and then 1/2 plus 1. This is going to be plus 1/2 plus 1/2. So this is going to be 2 radical u. Boom, bada bing. We're good. So, apply everything we know to this bad boy. Multiply that 1/2 in later. So u minus 4 times 2 radical u minus 2, and then this is going to be du radical, oh, why did I write that backwards? Radical u du. Okay? We apply the same concept we did earlier in relation to how to handle radicals and stuff like that. So u to the 1/2 plus 1, 1/2 plus 1, right? So now we have negative 2 times u to the 3 over 2, 3 over 2, and then because this flips over as a fraction, you're going to have negative 2 times 2 over 3 times u to the 3 over 2. Now I'm going to bring all of this up there to simplify everything, because I don't want to have to worry about everything anymore. So, put this all right here. If I multiply the 1/2 into everything, I'm going to get u minus 4. And I'm actually going to just go ahead and put in the r to what it's supposed to be, because I don't want to have to worry about it anymore. U minus 4 is equal to 4 plus r squared minus 4. Hence, r squared times the radical of this, which is just 4 plus r squared. And then it's going to be minus 2 times 2 all over 3. But this is multiplied by 1/2. So then this just becomes 2 over 3 times u to the 3 over 2, which is just 4 plus r squared 3 over 2 plus c. Does that look good for everybody? Okay. Can you see that up there? I think you can. Okay. So I'm just going to go ahead and put in my 1 and my 0. So 1 for plus 1 minus 2 over 3. 4 plus 1, 3 over 2. 0, this is just a big fat 0. Minus 2 over 3 of 4 to the 3 over 2. So if I then simplify everything out, this is just radical 5 minus 2 over 3, 5 to the 3 over 2, plus 2 over 3, 4 to the 3 over 2. And that is the answer we want. So again, the answer to the integral of r cubed all over 4 plus r squared dr is equal to, if you're just looking for the family of curves, r squared times 4 plus r squared minus 2 over 3, 4 plus r squared to the 3 over 2 power. If you're looking for the actual boundaries involved between 0 to 1, it's square root 5 minus 2 over 3, 5 to the 3.5 power, plus 2 over 3, 4 to the 3.5 power. We're good. Alright, give you a little bit of time to take a look, see, and then we're going to go straight into the other ones because I don't want to waste your time. I'm in the middle of something.
Buenas noches, hijo.
Hi, Mom.
No te desveles del balde.
I know.
¿A qué horas entras a la escuela?
I get in at 10. I'm kind of in the
night.
middle of writing a video real quick. I'll see you in a bit.
Ok, no se te olvide
I
cerrar
know,
las
I know,
ventanas.
I know.
Bye, voy a poner la lavadora.
Yeah. Sorry about that. So this one is takes a little bit of brain power. So what we have here is cosine, and we have radical x dx. Okay? So what we got here is this. How do we handle a problem that doesn't look like anything we've worked on? Well, we're going to go ahead and handle it anyway. My hint to you, if you're just looking at this problem right now and hopefully not cheating and looking at the video and just doing the video, is that you use a U substitution and see what happens based on past problems I gave you that can let you see a certain pattern I was giving when I presented to you these problems. Okay? So, assuming you're not doing that, and you're just here to check, u is equal to radical x, implying 1 over 2 radical x, right? So now we get cosine u times 2 radical x du. This and this are congruent. Hence, cosine u times 2u du. That looks a lot like a product of two functions that you need to integrate. So then we have u is equal to 2u, or I would just call w at this point, is equal to 2 du. dv is equal to cosine u, and v is equal to sine u. So now with this in mind, we're going to have 2u times sine u minus 2 times, and then what we have here, sine u du. We kind of know what this is already. This is pretty straightforward. So plus 2 cosine u plus c 2u sine u. Applying what we know based on our actual supposition of what u was, you should get something like that. Okay? 2 radical x times sine radical x plus 2 cosine radical x plus c, and there are no boundaries on this problem. That's kind of how I wanted it. So take a look, admire, and transform. Okay? good. Gonna go ahead and